Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to take a look at light, and in particular, how light interacts with your body. Well, the first thing is, what is light? Well, we've already studied that a charge creates an electric field around it, and a current in a wire creates a magnetic field. Well, it turns out you don't need a current, you don't actually need any charges moving to create a magnetic field. The moving charges basically are dragging their electric fields with them, and so it's those changing electric fields that are creating the magnetic field. And if instead of creating a magnetic field, or instead of electrons moving, we have just an electric field changing, then we get a magnetic field. And further study showed that if we have a changing magnetic field, that will in turn create an electric field. So we can have this self-propagating type of situation where an electric field changes, that creates a change in a magnetic field, which then creates a change in an electric field, and so forth. We call this an electromagnetic wave, and that's what light is. Light is a propagating, changing electric, therefore changing magnetic, etc. Field. And that's what we call an electromagnetic wave. Now, one thing to notice about this is because it's not particles moving, transferring energy to other particles, we can transfer energy through empty space. And that's what an electromagnetic wave is. It can go through empty space, it can go through, well, anything that's transparent. You know, that's what light does. Well, I guess transparent for that type of electromagnetic wave. We'll get more to that. We'll get into that more in just a moment. Okay, so, well, what is light? Well, when most people hear light, they think of visible light. Okay, but light is often a word that's used to mean more than that. It means the entire electromagnetic spectrum. Okay, so here we see the electromagnetic spectrum, and we see this huge range here. And we see that only this one small little point is visible light. It's a very small amount, okay? And that small amount of the visible is visible light. The rest of this light, the rest of these electromagnetic waves, are other types of electromagnetic waves. Okay, and we classify those into parts. We got the radio waves and the microwaves and the infrared, and we get to the visible, and then the ultraviolet and the X-rays and the gamma rays. Okay. You know, of course, that's what Marvin the Martian shoots people with, right? Gamma rays.
This is a robbery!
Anyways, we'll talk more about why that is in just a moment. But we have this whole range of electromagnetic waves, or light. They're all just electric fields changing, causing magnetic fields to change. So what makes them different? Well, probably the most fundamental way to talk about their difference is in terms of their frequency. Although their frequency and their wavelengths are inextricably linked to one another, the frequency with which the electromagnetic field is changing determines which type of wave it is on this spectrum. So if it changes very slowly back and forth, well, then we have a radio wave. And if it changes incredibly quickly back and forth, then it is a gamma ray. Okay, so the wavelength is kind of the inverse of that, and so if we have a very small frequency going back and forth very slowly, that's going to create a very long wavelength. It could be miles long for one wave. Whereas on the other side, we have incredibly high frequencies, and therefore we get incredibly short wavelengths because it's going back and forth so fast. Now, this is all based on the fact that light travels at a specific speed. Okay, light travels at 3.00 times 10 to the 8th meters per second. Okay, that is incredibly fast. Okay, it means it can go 300,000 kilometers in 1 second. Okay. That's a long ways. Okay. So that we take that number, that's going to equal, the speed equals wavelength times frequency, We've got that from our waves, our study of waves. It's true of electromagnetic waves as well. And so we could do calculations to figure out what the frequency of some electromagnetic waves are, or what their wavelength is. If we know one, we know the other, because for all light traveling in a vacuum, or for all intents and purposes traveling in air, it's very slightly different for air, but we'll just use the same number for air or a vacuum. We can calculate one or the other if we're given one. Now, we know that we don't want to be under ultraviolet light very long. And we know X-rays are dangerous because they put that big lead vest over us when they're taking an X-ray, and they go stand behind a shield. So something must be different about those. Well, you would assume they'd have more energy, right? Well, but from what we know of waves, energy is determined by the amplitude, which is true for light as well. If we have a bigger amplitude, we have more energy traveling out from a light bulb or from whatever it is that's producing the electromagnetic radiation, the electromagnetic waves. So why are these types over here, why are they more dangerous? How could they have more energy if energy is determined by amplitude and the type of wave is determined by frequency? Well, there was a dilemma that came up back in 1887 called the photoelectric effect. And we're not going to go into that too much, but it was a dilemma. Light wasn't acting the way we would have expected it to, in a way that dealt with energy. And let's see, what was that? 18 years later, in 1905, Albert Einstein published a paper figuring out and explaining this, and it's been since pretty much proven that that's what's going on, is that light does not just travel as a wave spreading out, but it travels in individual little pieces of light called photons. Okay? And a photon is a little piece of light, a little particle of light. That's kind of a wave too. That's called the particle-wave duality of light, is that sometimes it acts like a wave and sometimes it acts like a particle. And so here we have this little piece of light, a photon, that's carrying energy in little packets of energy called photons. And each packet has an amount of energy that's determined by its frequency. So while the total amount of energy going out is determined by the amplitude, as for all other waves, the energy of a photon is based on the frequency. And here's the equation. The energy of a photon is equal to h, a constant, times the frequency of that photon, the frequency with which the electric field is changing directions, or the frequency with which the magnetic field is changing directions. Okay? So E equals hf. So what's h? H is a constant called Planck's constant. And that is equal to 6.626 times 10 to the negative 34th kilogram meters squared per second. Okay? So that number is a number that is a constant. It's kind of, you might say, the value with which the energy of light was determined to be in our universe. Okay? That's Planck's constant. As far as we know, true all around the universe. Okay, so if we take a piece of light and we shine some light at something, what's really happening is there's a whole bunch of photons that are heading towards that, and each of those gets absorbed separately. So why do we care about ultraviolet light versus visible light? Well, visible light hits our skin, and our skin is made up of molecules, which is atoms bonded to other atoms, and those bonds have a certain strength. Okay, that strength varies from a little under 200 to up to 900-ish kilojoules per mole, which if you change from kilojoules to mole to joules per bond, that's somewhere in the region of 3 to 15 times 10 to the negative 19th joules. So now, what energy of light does it take to break a bond? Well, that's pretty much energies that are beyond visible, and up in the ultraviolet. Okay, so why do we worry about ultraviolet light instead of visible light? Because visible light hits us and it gets absorbed, but it doesn't have enough energy to break a bond, so it just kind of heats you up. It makes you a bit hotter. That's why we like standing in the sun, because it warms us. Okay, but ultraviolet light, or X-rays or gamma rays, those photons, even if there's not a whole lot of them, each photon has enough energy to break a chemical bond. And so if the chemical bonds in your cells are getting broken, that can cause damage. And it makes your cells start to fall apart. Okay. Now, of course, the outer layer of our skin is dead, and so there's a whole other issues with that I'll let a biologist talk a little bit more about. But that's why we worry about the ultraviolet, is because they have the ability to break a chemical bond and therefore change the structure of your skin or eye or whatever they come in contact with. Okay. Now, X-rays have even more energy. They're more likely to pass through things. We know they can pass through, and we can see a kind of a shadow of our bones when you go and take an X-ray. So those X-rays can pass right through you, but the ones that are absorbed, those have a lot of energy, and they can rearrange molecules, which is why you don't want to be exposed to X-rays every day, and why the technicians go and hide behind that shield so they don't constantly have X-rays traveling through them, changing the molecular structure of their cells. Okay, so that's how light affects your body from a sense of the danger and the damaging. Now, of course, one of the things that you might be more interested in is, how do we see? Well, that's going to be our next video. So tune in next time to see how our eyes interpret color and how we see. So from a physicist's perspective. All right. Well, we'll see you next time on the Scientific Adventures of Beardman. Stay away from those high frequency waves. See you next time.